Okay, everyone, welcome to the NX Multi-Access CAM webinar. This is the second webinar in our digital machine shop series. The first one was NX Mold Tool and Die. And if you weren't here for that, or didn't hear about that, you can find that recording of that webinar on our YouTube channel. So please go ahead and check that out. In the next couple of months, we will be having the third installment of this series on highly automated CAM. So look for details on that to come. I want to welcome our presenter today, Jim Hughes from Siemens. He is an expert in this, and we are excited to have him present today. I did want to ask that you all click the three little dots at the top of your screen and choose to view this full screen so that you can really take advantage of all of the intricacies of what Jim is going to be presenting today. Also, I will have the chat open, so if you have any questions, please put them in the chat and we'll take time after the end of the webinar to answer all of your questions. So thanks for joining us today.
Okay, thank you, Kim. Again, I'm Jim Hughes with Siemens. I've actually been with the Siemens PLM group for over 25 years. Been doing manufacturing for 40 plus years, so have a pretty good knowledge of most of the NX CAM topics that we'll run into. If you try, you can stump me occasionally, but I could answer most of your questions. So with that, today we're going to be talking about multi-axis milling. Most of the enhancements that I'll show were released in the NX 2007 version, which was released back in December of 2021. It's also worth noting that some of the items I cover today were in previous releases, such as NX 1980 and earlier. So you'll get a pretty good flavoring of what's new. Topics I plan on covering today is the multi-axis deburring, multi-axis roughing operations, multi-axis rotary roughing and finishing operations, 5-axis guided curve, 3 to 5 axis tilted tool axis, turbomachinery, and tube milling enhancements. So again, most of what I'll show is multi-axis, 4 and 5 axis, and we did a previous presentation on 2.5 and 3 axis earlier this week. That is, I think, available as a recording. So jumping right in. First thing I want to talk about is multi-axis deburring. We also have planar deburring, but right now we're going to talk about multi-axis. The multi-axis deburring will let you do 5-axis, 4-axis with rotary, 4+1 rotary auto tilt. It'll do 3-axis and 3+2 axis deburring operations. All these operations do use ball or spherical end mills to deburr edges of your part. Your automatic tool tilt ensures tool orientation is safe and smooth, and use your 5-axis deburring to deburr edges excuse me, and transition simultaneous in 5-axis. One thing to note that the edges can automatically be detected or they can manually be selected. And this operation is recommended for multi-axis deburring when your chamfering and fillets are not modeled. With that, I'll show a little video.
Multi-axis deburring enables you to create 3, 4, and 5-axis edge deburring operations where chamfers and fillets are not modeled. It supports faster part programming by automatically detecting edges and tilting the tool axis based on user intent to provide safe and efficient tool paths. Multi-axis deburring supports ball and spherical tools. Use 5-axis simultaneous to deburr edges and transition simultaneously in 5 axes. Use 4-axis rotary to deburr edges in 4 axes with the tool normal to a rotary axis. Use 4+1 axis auto tilt to deburr edges simultaneously in 4 axes around a rotary axis and transition between edges by tilting in 5 axes. Use 3 axis to deburr edges and transition the tool along a fixed orientation. Use 3+2 axis to deburr edges along a fixed orientation and transition between edges using 5-axis simultaneous motions. Let's take a look at some of the operation parameters that are available. For multi-axis deburring under mill contour, the tool axis intent is set to 3-axis by default. 3+2 axis is now available. 3+2 axis is similar to 5-axis tilting. The difference is that the system tries to keep the tool axis fixed as much as possible. Collision checking can change the tilting to 5-axis simultaneous when necessary to avoid collisions. Fixed to main axis is now available for basic alignment when using a 3+2 axis and 5-axis simultaneous intent. This option uses the specified tool axis as the main axis from which to reference the tilt and maximum angles. In this case, the positive ZM axis is referenced. The tool axis remains at a fixed angle to this axis, but can tilt away when needed. Collision checking can tilt the tool away to avoid collisions. Blend spline is a new transfer type available for all tool axes. This option uses a spline to create a smooth transition between cutting moves. Blend spline will usually reduce the tool path length and hence the machining time. Several clearance options have been added. These options create an automatic safe clearance from the part geometry, the same as they currently do for other variable axis operation types. The available clearance options vary depending on the specified tool axis. Relief has been added to the inner corners options. Relief extends the tool path to deburr inner corners without adding a loop. Detect by height allows you to machine sharp edges in a specific area. The vector defines the reference axis, which specifies the direction in which the area will be limited. The start point defines the position with respect to the reference axis from where the limited area starts. The end point defines the position with respect to the reference axis where the limited area ends. Only sharp edges between these boundaries are considered.
Okay, so that is the multi-axis deburring. I can actually show some of that live if you want. We can here in a bit, but I'm going to go ahead and with the next slides and we'll jump to that later on when I have a part open. So next we're going to talk about multi-axis roughing operations. So when you're dealing with mold cavities or prismatic shapes, there's a fast way to remove material using the high-speed adaptive roughing cycles. The 5-axis process, you can get closer to your semi-finished shape of your finished part and significantly reduce the finishing cycle times. With the adaptive milling, the tool cycle time reductions can be dramatic. And I've seen some by 60–70%. With the adaptive milling, you'll reduce the radial depth of cut, otherwise your side stepovers, to less than 25% of the tool diameter, but significantly increase your axial length depth of cut. What this will give you is a smaller chip thickness, and basically you're going to have increased feed rates because of that, if you can increase the feed rates because of that. So this will result in a light, fast cutting action and will enable more aggressive cutting. And like I said, generate up to about probably 60% reduction in cycle times. So here was a little video that just showed some of the roughing. This one is very quick. And like I said, that was just a real quick little video. Here was another one. This one was done by Sandvik, one of our partners. And what they noticed was at the end of the tool, it lets them use a lot shorter tool. And at the end of the cutting, they noticed minimal tool wear on this. So these are some of the advantages on doing the adaptive milling and the 5-axis roughing. Okay, another one I'd like to talk about would be the rotary roughing. Rotary roughing, basically, it's it's been around a few releases, but it allows users to quickly and easily create a part using 4-axis rotary machining process. The users can specify the part geometry, your cutting tool, optimize path and cutting parameters, and get an efficient tool path fairly quick. You also note that one of the enhancements, you can now use specify either a flat, a ball, or a bullnose end mill. When this was originally released, I believe it was only just ball mills when you were doing the rotary. Basically, the system detects the material and removes based on part and blank bodies. And then the part process can be optimized by specifying your contact shift for the tool. And we'll see some of that in a short video here in just a moment. And last item I want to note is that path can be a combination of follow part and helical motions. So with that, I'll launch a little video here.
You can now create rotary roughing operations for cylindrical and conical parts. This new operation type supports ball, bullnose, and flat end mills. Let's begin by looking at operations for a cylindrical part. It's important to correctly define the axis of rotation, in this case, the positive ZM axis. Each successive concentric level is removed using a follow-part helical cut type. Cut levels are measured from the IPW. When an obstacle is encountered that interrupts the helical motion, the motion switches to follow part using a zig pattern. Pockets are machined using the follow part inside-out motion. An end view shows that the last cut level does not reach the bottom of the pocket. Top-off critical depths allows you to further control the cut depth by specifying a minimum cut depth as a percentage of the specified cut level distance. 0% minimum distance allows the tool to cut all the way to the bottom of the pocket. 85% minimum distance prevents the tool from cutting into the pocket because the depth of the pocket is less than 85% of the specified cut level distance. All levels above are cut at the specified distance. Limiting the machining range allows you to determine the beginning and end cut levels of the range. Limiting radially allows you to restrict the machine depth between a minimum and maximum machining radius. Limiting axially and radially allows you to limit the machined volume to the specified axial width and radial depth. Limiting axially allows you to limit the range along the axis of rotation. Radial limits can be defined easily by dragging start and end cylinders concentrically. Axial limits can be defined by dragging start and end planes along the rotation axis. Smoothing eliminates sharp corners. Infills and finish passes smooths sharp corners on all but the final pass, allowing maximum material to be removed from the part walls. Depth first cuts each region from top to bottom before moving to the next region. Level first moves from one region to the next before repeating the sequence for the next level. Bottom-up cutting between cut levels allows you to optimize cut depths and volume by cutting intermediate levels from the bottom up. Rotary roughing operations can also accommodate cut levels for conical parts. The conical rotary depth mode allows cut levels to follow the conical shape of the part. Without this option, the cut levels would remain parallel to the axis of rotation, cutting deeper and deeper by steps as the cone narrows. Cone angle is measured relative to the specified axis of rotation, in this case the positive ZM axis. This value should reflect the conical shape of the part. In this case, the cone angle is -9 degrees. The result is a smooth, continuous 4-axis tool path with cut levels that follow the angle of the cone.
So as you can see, the rotary roughing has some real benefit there, and it has been greatly enhanced over the last few releases. They keep adding to it. Next thing I want to discuss is rotary finishing. For this one, it's very similar to rotary rough. Basically it's a specialized 4-axis machining for rotary parts with cylindrical floors. On this, it only rotary finishing only supports ball end mills. It doesn't allow you to use a bull nose or a flat end mill for doing the finishing operation. And then the operation subtype only supports zig or zigzag cut patterns. So it's important to know that. You can use tilt tool axis and get 4-axis rotary motion with lead angles if you need to. As the little image shows there, you can have lead angles on it. Next thing I'd like to discuss is the 5-axis guiding curve. The first one I want to talk about on guiding curve is the multiple depths. 5-axis guiding curve multiple depths enables the cutting depths within a single guiding curve operation to basically efficiently remove volumes of material at multiple levels. Let's see what else we want. Let's go ahead and now I've got a little video for this one.
Variable guiding curves operations can now generate multiple cut depths, allowing you to remove material by machining toward the part geometry one cut level at a time. The multiple depths options are new. When turned off, multi-depth cut generates a single cut level that follows the part surface contours as variable guiding curves operations did previously. Part stock offset does not apply when multi-depth cut is turned off. Here you can see the tool is embedded. This can be solved by specifying multiple cut depths. When turned on, multi-depth cut generates multiple cut levels, removing the specified part stock offset by the specified increment or number of passes. Cut level depths are applied by offsetting the original tool path along the tool axis. The tool is essentially pulled along the tool axis at any given point. Increment specifies how much of the part stock offset to remove for each cut level. If the specified increment does not divide evenly into the part stock offset, the system reduces the stock removed in the last cut level. Passes specifies the number of cut levels. The system calculates the depth of cut. In this video, we'll look at a sequence of operations, each containing an edit that improves the efficiency of the original multi-depth toolpath. By doing so, we can also compare improvements in the operation machining time. In this multi-depth operation, you can see the tool cut's error. This can be solved by specifying Use 3D for the in-process workpiece. Use 3D restricts cutting moves to only those that remove material. Cutting moves that do not remove material are omitted from the toolpath. When Apply to Last Pass is turned on, the final cutting passes closest to the part will only be made where there is significant material to be removed. When turned off, the finished passes closest to the part are cut entirely, whether or not there is significant material to remove. This is done to avoid lifting the tool on and off the final part surface, which might degrade the final part finish. Notice that lifting occurs in other areas where there is little material to remove. This can be solved by specifying the minimum amount of material to be removed. Minimum material removal prevents the tool from lifting where there are small amounts of material, allowing for a continuous smooth cut. Notice there are an excessive number of engages and retracts. This can be solved by specifying a merge distance. Merge distance connects non-contiguous cutting segments to create continuous cuts without retracting. The tool path can be further improved by alternating cuts from the outside in. Setting the cut order to outside in alternate allows the tool to move smoothly from one cut pass to the next. Notice how the machining time has improved from the initial multi-depth cut operation.
So you can see there that originally the machine time was 2.5 hours or so. And with the improvements that we did walking through those changes, it was down to 47 minutes. Significant difference. Next, we'll talk about 5-axis guided curve tool axis interpolation. The tool axis interpolation has been around, but it was typically you would interpolate in one direction only. And the new option that we're going to be talking about here in a minute is that you can do both in X and Y vectors. So this option basically, it gives you control that you're going to interpolate the tool axis along the drive pattern direction only. Then you'll see what the path looks like, and you can see your vectors are kind of going different directions. Next, we have, so here it is along the drive. Now we're doing along the drive control direction. And again, you can't change the number of vectors or the location. It basically doesn't have any impact on these when you have just one vector going on. So again, this is existing parameters that we had previously. I'm going to get to the one here in a moment that we did not have. Here you can now control interpolation normal to the drive and then across the pattern. And again, number of vectors or their location doesn't impact the behavior much on this. So the new UV that you can select, this will allow you to control it in both directions. And we're going to show a little video in a moment that'll show the improvements. If you only have one vector, you'll get a fixed axis toolpath using the specified vector. If you have two vectors, then the system will interpolate between the two vectors, one direction either along the drive or across the pattern, depending upon where the vector is selected. If you have 3 or more vectors selected, then the system will interpolate both along the drive direction and across the pattern, and will formulate a UV grid based on the user's vector selection. So I'll show that here now in a little video.
For variable guiding curve operations, Tool axis interpolation can now be controlled in both the U and V directions. This provides better tool axis control, which can result in smoother tool paths and better surface finishes. In this example, tool axis interpolation is currently controlled only in the U direction. Notice how the tool axis swings from side to side because tool axis interpolation in the V direction is not controlled. The U and V control direction option is new. Tool axis interpolation is controlled both in the drive direction and across the pattern. As with other control direction options, you may select points and adjust the axes. The result is a more controlled tool axis.
And again, this is the U and V controls on interpolated tool axis is new. And I think it's a significant enhancement for folks that are using interpolated tool axis. Next, again, with 5-axis guiding curve, we're going to talk about wall stock. The wall stock in variable axis guiding curves is primarily intended to avoid the neighboring walls that are either one, not machined, in which case we don't want to embed the tool into the stock, or we have previously machined walls and we do not want the tool bumping into or contacting the finished surface. Most common case for it is to select the wall perpendicular to the cut or guide edge and wall geometry, and then specify the wall stock to limit the amount of tool lead in and run off. So let's look at this little video.
Variable guiding curve operations can now use wall stock to avoid embedding the tool or contacting unfinished walls. This can result in longer tool life and better surface finish. While NX can currently tilt the tool away from the wall, wall stock offsets the tool by adjusting the tool path within the cut area. Not applying wall stock may cause the tool to contact the unfinished wall, potentially compromising the surface finish. The specified wall stock is applied to all selected walls.
Okay, and that's just a little quick video on wall stock. Next, I want to actually shift to the 3 to 5 axis tool path conversions. That has been around since NX 8.5. It was originally reduced. It's had several transformations along the way. They greatly enhanced the capabilities in NX9, and then we're automatic with the automatic tilting, and now we can do it for 3-axis roughing. One of the real benefits of this is being able to program a part as a 2-axis part, or I'm sorry, as a 3-axis part. So you turn off collision checking and just program your part, either a variable or a fixed axis. Let it go ahead and collide, and then all you do is go onto the tool path and tell it to tilt the tool axis, and it will create you a 5-axis path that will be safe to run, and it will clean up the collisions that you're going to have. So with that, here's just an example. You can see here was the path, the variable axis. Before I tilted it, I was hitting on both of these walls right here on both sides. After I tilted, it automatically moved away and did not run into the part. So with that, let me go over to here. Let's do something live here. So let's start with this part. Fairly simple. This looks like the one that we just saw. If I come up here to this tool path and tell it to verify, you can see right now there is a collision right here with this wall. If I come over here, you'll see the same thing. It's colliding. That's because when we created the operation, we have collision checking turned off. But we went ahead, created the operation. All we have to do is go to tool path, tilt tool axis. I'll just take the default settings in here for right now. And the default settings usually will get you pretty close to what you want without any changes. Now you'll notice it has tilted this away, and if I'm over here, it's tilted away too. So I can actually tell it to just go play this tool path, and you can see that it has now tilted that tool path for me. And that was fairly simple. The idea is that if you don't know how to do 5-axis and trying to get an operation to do that fairly quick, might be a little bit difficult, but you can just create your 3-axis. Don't worry about the collisions, and then let the convert tool axis, tilt tool axis, convert it for you. Okay, another example of the tilt tool axis is, well, sorry, I switched parts and forgot to get out of the verify first. So here I just created a simple Z-level profile. We can do it from scratch, I guess, if we wanted, but all I did here was under my geometry, I just specified the part, the whole part. I then went into my collision checking, and I turn those off typically, okay? Generate the tool path. Oh, I'm sorry, turn those off. If you have them turned on, they don't generate it. So there's my tool path. If I'm verifying that fairly quick, I can go down through here, and you'll see about the second, third pass, it starts colliding with the tool. So I will jump one ahead a little, but you can see I'm colliding with both the tool and the holder here. So fairly simple. Again, this was just a standard Z-level profile. I can go in here, tell it tool path, tilt. We'll take the default settings for now. Takes it a moment to regenerate. Now, if I go back into verify, I've got a tool path that has been tilted and is collision free. So this is, like I said, using just a 3-level Z-level operation. It also, I used one that was a variable axis that I had collisions in. I could actually do the tilt, and it will then clean it up so that you will not collide as you're doing this cut. I would have gotten warnings if I had any collisions down here in these last few passes. Last pass here. Okay, I have one more on the tilt tool axis that I want to show, and then I'll move on. Here I've got just it's a contour area, not tilted at all. If we go in to look at our verify here, if you pick any of these corners, you'll see there is a collision with the holder and the Well, it's going the other way. But anyway, it's got collisions. So what we'll do is same thing I just did. Go over here, toolpath, tilt. Fairly quickly, I've tilted this toolpath. Now I can come into my verify. And if you say play, you'll notice that it's tilting and I am now not colliding anywhere on the path. So that's it for the tilt tool axis. Very handy for especially for folks that are not real familiar with creating multi-axis paths. They can create these as 3-axis, don't worry about collisions, and then come back and NX will automatically calculate and avoid collisions with the tool and clamps and the part and the tool holders. Okay. With that, let's go back over to the presentation. The next thing that I wanted to talk about is Turbomachinery. Turbomachinery is the for doing impellers and blisk. Basically, you can do impellers with multiple splitters. It'll handle all these curved and weird and wonderful impellers that you would do. There's not any restrictions as far as whether it's solid bodies or sheets. Personally, I like working with solid bodies. I think you run into problems at times with sheets, but we don't have that requirement on the turbo machining. You can work with surfaces. And then if it's got gaps or overlaps in your actual geometry, it'll heal them automatically. It does support IPWs, in-process workpiece, and it does do holder collision checking and avoidance. And then it'll do smoothing on your tool paths. Geometry for doing impellers is you go in, you define your hub as the floor down here. The shroud is the outside edges of the blades. Then we will get on the blade sides of the blades here. The blend is at the down at the hub where the blade contacts. That's a blend radius it'll put. And then it'll handle splitters, and you can do multiple sets of splitters. A lot of impellers will have shorter blades in between your main blades, and those are referred to as splitters. And so when we define the geometry, you go in and tell it the splitters, and you can set multiple sets if needed. Then next, we'll talk about operations. The operations for Turbomachinery, you'll have roughing. That's it's going to basically rough out all the area between the blades. You can also do an operation type for rest milling. If you need to come back with a little smaller cutter to clean out some corners, it will handle that and do that for you. There's hub finishing. That is finishing the floor of the down between the blades. And then you've got your blade finishing the walls of the blades. You've got your blend radius down at the bottom, finishing that. And then you're doing your edge finishing out on the shroud, out on the outer edge. And those are all different operation types that actually show up in the multi-blade template. Sorry. So with that, instead of showing this video, I'm actually going to go back to NX and let's go over here to this impeller. So here's one that already has operations, but first thing I would do is I come into NX with this, and I would then go to my geometry. Under the workpiece, I typically say insert. I'm not going to do this, but I will start. I'll do insert geometry. Go to your multi-blade. And you'll notice here's the dialog that pops up. So we would do the hub, which is down here. Then we'll go to the shroud, which is this outside edge of the blade. Then we would do the blade right here. Just the sides of it. Then we'll do the blend down at the bottom of the So we've now got all of this defined. Splitter, this one has one set of splitters. So we would then say, well, the walls for the splitter is right here. The blend, again, is down here at the hub. And you'll notice there's just one in here. If I did an impeller that had more than one splitter, you would hit the plus here and go and add another set and go define your next splitter. Say okay to that. We tell it there are 6 blades, and they are around the Z-axis. And that means you're counting these large blades, not the splitters. And so if you look, that is exactly what this operation has in it. Okay. So the first thing you would do then is you would do the roughing. And it basically, when you generate it, it very quickly will generate the tool path for this. And again, I just took default settings as I was doing this. So then if I say I want to verify this tool path, 3D, so fairly quick, you can, let me slow that down just a couple. So fairly quick, you can actually rough out this first blade here. Then we do a blade finishing operation here, and you can see it's actually doing the cutting on the blade. This opposing was they were actually showing just, they finished one side here and one side there as they were doing that, as opposed to doing all the way around one. Personally, I like to go around one blade at a time, but there's people that want to be able to do it the other way, so you can. Then there's the finishing on the splitter. Here's our hub finishing. There's our blend radius around the blade, and then you got the blend radius around the... So if I actually just ran all that, now what I typically do is I go create this roughing, then I go and do an instance of those 5 times around. So then I'm doing the roughing of the whole thing. Then I will come back and start doing my finishing operations. But you can do it just like this and run it if you wanted. And if I say just suppress the, well, that's going to take a while if I do that. But it'll basically do all the roughing, and I've got it turned up so it goes fairly quick. Excuse me. Years ago, I was at IMTS, and we were standing there looking at a fryer machine where we had programmed a part that was cutting an impeller similar to this. And as we were looking, a guy come up and was looking at it, and he goes, "Oh man, I bet that was a real bear to program." And I looked at him and said, "Well, you can do it in about 10 minutes." And he goes, "Oh no, so no way you can do that in 10 minutes." So we walked over to a booth that was close by, and there was one of our guys had his laptop there. So it wasn't even my laptop. Went over, opened up the impeller that was in the samples folder, and proceeded to go into NXCAM, define my geometry, define an end mill, create all the tool paths. And we were about 9 minutes in as it was doing the verify. And he goes, "I believe you can do that." Now he was sitting there with his iPhone taking a video the whole time. I'm going to stop this. But I mean, you can see it runs through all those, and then it's simple enough to go instance the path so that you're do the other 5 and put it in order, and then you're posting it. And so 10, 15 minutes, you can do a very complex part like this, which, excuse me, which these are complex. This is a very specialized package, and it actually does a very good job on blisk and impellers. So with that, we'll go on to the next topic. Let's go back here. And I figured instead of showing that in a video, I thought it was better to show it live. This one is tube milling enhancements. The tube milling operations, 5-axis operation for cutting narrow, hollow features, regions with closed cross sections, including ports for engine blocks and heads and stuff, is primarily where this is. The built-in expertise lets you quickly create efficient multi-axis roughing and finishing operations on these type parts. And then basically, additionally, NX gives you precise control over the tool axis to create the most efficient operation for these type parts and challenges. So a couple of operation types that you will have in your dialogue are the tube rough, and that's basically for doing your roughing. It's intended to be used with a spherical end mill only. And then the tube finish will let you use a spherical or a ball end mill for doing the finishing. So with that, I got a little video I'm going to launch, and
tube roughing and tube finishing operations can now.
Sorry.
Creates a central curve automatically based on the specified cut area. The Preview Central Curve and Create Central Curve options are new. These options are available only if the cut area has been defined. Preview Central Curve displays the calculated central curve based on the specified cut area without actually creating the curve. Create Central Curve creates the curve geometry as an object inside a group in the Part Navigator. Cutting parameters now allows you to control edge rolling without creating or modifying geometry. The Extend Path Entry Side and Extend Path Exit Side options are new. The edge rolling percent value extends the cut level at each end of the tube by a percentage of the tool diameter. This allows you to extend the cut area past the part surface on the high side while completely finishing the area on the low side. The edge rolling percent values must be between 0 and 100%. Currently, the entry side edge rolling percent value is set to 0, causing the opening of the port to remain partially unfinished. Changing the entry side edge rolling percent value to 100% extends the cut area, causing the opening to be completely finished.
Okay, and that was just kind of a quick demo on tube milling. Whoops, I was going to come back over here, and I did want to show one additional thing that we had talked about, and that was, and I thought I had it open, but I didn't, so let me get it open. We talked about the planar deburring, or about the deburring, and so I wanted to show it to you. Fairly quick and easy. I can create an operation from scratch. We will go to multi-axis. We're going to do the deburring. And I'll say OK to this. Geometry. Right now, I basically, it's my part. It has been selected. OK. There are no excluded edges at the moment. If I hit generate, it will go and try to it'll create a tool path on all of the edges. Well, there's a few edges here I want to eliminate. Like I really don't want to try and cut between the part and the jaw here. That would be a bad idea. But so very quickly, I can start eliminating some of these edges just by picking them. And I got one more there. Get that guy. So with that, I'll say OK, and we'll go generate that toolpath again. And here is your multi-axis deburring on a, if I click the button this time, on a 5-axis part. And you can see, if I say do a verify on this, I've now fairly quickly created, whoops, I didn't want to do the material removal there. That was, I've just done do a replay. Okay. So there was an example showing the 5-axis. Again, you can do it as a planar deburring operation if you just want it all to be 3-axis. But this is, you know, a new feature and functionality where you can do this 5-axis. And with that, I will go back over here, and that was all of the content that I had. And we're ready to go to questions and answers. In case you guys have any questions, I'd be happy to try and answer or show you anything that that you wanted to see that I didn't show today.